We're going to start off like we usually do with each unit. We've got several definitions, okay? A probability experiment. Is a process that leads to well-defined results called outcomes. An outcome is the result of a single trial of a probability experiment. Okay. A sample space is the set of all possible outcomes of a probability experiment. And an event is any subset of the sample space of a probability experiment. Okay? Now, like I said, these are just some vocabulary terms. We talk more about these, though. We actually use these when we're finding probability. Okay, so a sample space is all the possible outcomes, guys. Okay, such as if you flip a coin one time, what's your possible outcome? You can get tails, you can get heads. If I roll a die, and guys, the proper word is die, that is singular, okay? You roll dice if there are multiple die. One is a die. More than one is dice, okay? You usually think of it as dice because when people roll dice, there's usually two, so they're dice. But one die, if you roll one, what are the possible outcomes? That sample space is you're going to roll a 1, 2, 3, 4, 5, 6, okay? An event is the subset of that sample space. So if I asked you, if we're looking for the number of how many even numbers could I get? I could get 3, right? 2, 4, and 6 occur. Those are 3 events that happen in that sample space, okay? We talk about 2 different types of probability. There's theoretical probability, and then there's what we call empirical probability, and empirical is just experimental probability. But we start off talking about the theoretical probability, okay? So formula for theoretical probability. Okay, let E be the event in the sample space S. Okay? The probability that an event occurs And we denote that with P parentheses, capital E, close parentheses. And that capital E will be replaced by what we want, okay? So like the probability of rolling a 2 or the probability of rolling an even number. That'll go inside the parentheses, okay? It equals the number of outcomes of E divided by the number of outcomes of S. So that's just the total number of outcomes in the sample space, guys. So when we calculate these things, what we need to do, of course, is we got to find out who all's in the sample space. We got to have how many outcomes are in the sample space. Then you can calculate how many events are in there because you just look, okay? It's not bad. All right, let's look at example 1. Each number from 1 to 12 is written on a card. And the 12 cards are placed in a box. One card is picked at random. For the 4 events listed below, compute each probability. Okay? A 7 is drawn. B, an odd number is drawn. C, a number less than 4 is drawn. And D, a number greater than 7 is drawn. Okay? All right, so the first thing that we want to do is we need to find out what's in my sample space. Okay? All right, well, what does it say we did? We took cards and we wrote the numbers 1 to 12 on each card. Now, we didn't put 1 through 12 on one card and do that multiply. We put a 1 on one card, 2 on another card, 3 on another card. So how many cards do we have? 12. So I went around and I got a box and we put those 12 cards in there. Now, you do not have to draw a picture every time you do a sample space. I do it just so you guys can see what I'm talking about, okay? Many of you don't need to actually visually see that sample space, but there are some of you that do, okay? And the more of this you do, you don't have to draw it. You see it in your head, and it's good to go. Okay, so we got this box that got 12 cards, each with the numbers 1 through 12 written on one per card, right? Let's shake up the box. It says, I want to know the probability of drawing a 7. I'm going to put my answers in green down here. So the probability of 7 is going to equal, well, the first thing that I list in that denominator is the number of total outcomes in the sample space. How many different outcomes are there in the sample space? How many cards are in the box? Yeah, 12, right? There's 12. Okay? Now, what goes on top is the number of outcomes of E. Well, how many 7s are there? 1, right? And only one of those cards contains a 7. So the probability of drawing a 7 is 1/12. Okay? B, I want the probability of an odd number. Okay, well, once again, how many are in the sample space? 12, that's in the bottom. Now, I need to know how many odd numbers there are in that box. 1, 2, 3, 4, 5, 6, that's correct. You have the chance, 6 chances, possibilities of getting an odd number, right? 6 out of 12. So the probability of you drawing an odd number is 1/2 or 50%. That's not bad. Okay. C, a number less than 4 is drawn. Okay, so the probability that we have a number less than 4. Okay, number less than 4. So I go up here, well, once again, denominator is going to be 12, right? It's the possible outcomes. I need a number less than 4. So 1, 2, 3. I have 3 chances. 3 out of 12, 1/4 is my probability. You need to make sure that you simplify that fraction. Okay? So about a 25% chance of drawing a number less than 4. Okay? And then D says I want a number greater than 7. So the probability that I have a number greater than 7. Okay? I'll use yellow. So I've got 8, 9, 10, 11, 12. How many is that? 5 out of 12, right? Okay. Nearly 50%, not quite. Your largest probability is drawing an odd number because that was 6 out of 12. That was 1/2. It's 50%. 5 out of 12 is not quite 1/2. You're a 12th away. Okay. Good job. That's example 1. Example 2. I'm going to flip to the next page. Example 2 says, suppose that in a certain game, it's equally likely that you will win. Lose, or tie. Okay, we want to find the probability of A, losing twice in a row. B, winning at least once in 2 tries. C, having the same outcome twice in a row. Okay, so here's what we have. The first thing we got to do is we got to determine what that sample space is. And guys, generally that's the most difficult thing for you is determining the sample space, how many outcomes are in that, especially on a problem like this. Okay, so if I'm looking, let's talk about that first. You go up to a machine and you get 2 plays at this machine, okay? You can play 2 games. I mean, it's quick, okay? The first time you play the game, you can win, lose, or tie. The second time you play the game, and you go, okay, so they give you a L, W, or T, okay? And they go, okay, hit it again. And you hit it again, and you either get an L, W, or T, okay? That's what this scenario is about. So, you first need to, in that sample space, you need to write out all the possible combinations, possibilities you could get. You could win, right? You could win the first time, and then you could win the second time, right? You could win. You could get a win-win. Couldn't you? You could get a win, and you could get a tie. They could give you a WT, okay? You could get a win, and you could get a loss. That's all the ways that we can win the first game, okay? If I win the first game, I could win the second game. If I win the first game, I could tie the second game. If I win the first game, I could lose the second game, right? Well, let's talk about if I tie the first game. I could tie the first game and win the second one. I could tie the first game and tie the second one. I could tie the first game and lose the second one. Couldn't I? Okay? Let's do the same for if I lose every first game. I could lose the first game and I could win the second game, right? I could lose the first game and tie the second game. Or I could lose the first game and lose the second game. Those all the possible scenarios that could occur when I step up to that game and I get to hit twice. I could win and I could win. Probably not going to happen. I could win and I could lose. I could win and I could tie. Or I might tie and win. Then I might tie and tie. I might tie and lose. Might lose, win. Lose, tie, lose, lose. Okay? How many possible things can happen there? How could it go for me? How many possible scenarios could happen for me? 9. Okay? That sample space has 9 different events that could occur there, is what that's saying. Okay? So A, when I go to answer A, it says I want the probability of losing twice in a row. We're playing in a row anyway. Okay? So I'm looking for losing twice. So an LL, how many times do you see LL happen? 1. And there's a total of 9 possibilities, right? So my probability is 1 out of 9. Okay? B, probability of winning at least once in 2 tries. Okay? Well, you know, there's 9 on the bottom. It's 9 total. It says at least once. So I need a scenario where I have at least 1 W. I can have 2 W's. That's 2 wins. But I need at least 1 to count it. So a win-win counts. Okay? A win-tie counts. A win-loss counts. A tie win counts because there's at least 1 win there. Okay? and there's a loss win counts, right? So there are 5 out of 9. That's not bad. You got a 50% chance, over 50% chance, because 4.5 out of 9 is half, is 50%, and this is 5. So you've got a little over a 50% chance of winning at least one time. Okay? Not bad. All right. C was the probability of we have the same outcome twice in a row. Now, that's pretty easy to pick out since we wrote them all out. So we're looking for the same letter both times. The win-win, loss-loss, tie-tie. How many is that?
3 out of 9.
3 out of 9. And you need to simplify that to 1/3. Okay? Now, the next things that we write down, they are important because you will have, I think the first 6, 7 questions of your homework involve these important observations about probability, okay? So, we have important observations about probability. Okay? Probability is never negative. Okay? If you get a negative probability, guys, you're wrong. Recalculate, okay? Like your GPS does, recalculating. Probability is never greater than 1. Guys, that means you shouldn't ever have over 100%, okay? When you find probability, you're finding the fraction, which is really a decimal, which is really you can turn into a percent, right? Okay, you shouldn't get over 100%. Like if it asks you for the probability and to express it as a percent, you shouldn't be getting anything over 100%. Okay, you shouldn't be getting anything over 1. You'll always get you should always get a decimal back. Okay, decimal less than 1. When an event can't possibly occur, when an event can't possibly occur, its probability is 0. Okay, let me give you a scenario because some of you are going, how can something's probability be 0? I have a 6-sided die. I roll that die. What's the probability that I get a 7? If it has 6 sides and it's numbered 1 through 6, I'm not ever going to get a 7, am I? I can roll for the rest of my life and I'm not going to get a 7. So the probability of me rolling a 7 is 0. Okay? When an event is certain to occur, the probability is 1. Okay? Those 12 cards I had before, let's say I wrote the number 12 on all 12 cards, and I asked you what was the probability of drawing a 12. That would be 1. You're not going to get anything else except a 12. Okay? If you add, last one, if you add the probabilities for every outcome in the sample space. The result is always 1. Okay? Those are important. You will have homework questions over those. If any of you have sat in statistics before, you know these are very important. You had questions that focused around that in statistics also. Even if you took AP Stats, you had questions that talked about this in there. Let's talk about the probability of a complement. Do we remember what a complement is? That's back from set theory. Remember, it has the little tick mark at the top. That's everything that's not in that set. Like if I ask you for the complement of A, it's everybody that's not in the circle of A. We had our Venn diagrams, we'd have A, B. I'd ask you for A complement, and we shade all around and then write all the numbers around there, okay? That does come back to haunt us here. The probability of a complement for any event E if the complement of E is the event E does not occur, then the probability of E complement equals 1 minus the probability of E. This does become important once our data in our data set grows much larger, because sometimes it's very difficult to count all the events where something is not happening. So it's easier to go 1 minus the probability that it does happen, okay? And the next example deals with that, even though it can be done using our normal counted up, okay? All right, I'm gonna let y'all get that copied down. And then I'll flip to the next page because example 3 takes about half a page. And then we'll talk about empirical probability. Okay. Example 3 of the next 32 trials on the docket in a county court. 5 are homicides. I said this must be in Harris County in Houston. Because that's about right. No, yeah, I lived there for 4 years. 12 are drug offenses. 6 are assaults. Actually, the assaults would be higher. 6 are assaults, and 9 are property crimes, and they don't even worry about those. See? Homicides would be higher, drug offenses would be higher, and the assaults would definitely be higher. Assaults would be high because domestic disturbance falls under assaults. Domestic violence would fall under there, so that would be quite higher in Harris County. 6 are assaults. 6 are assaults. 9 are property crimes. What's the probability that a juror gets assigned to a case that isn't a drug case? Okay? Now, of course, the first thing we're going to do is we're going to set up that sample space. And honestly, setting up the sample space is pretty easy here because they tell us how many total there are, and they tell us what each one of those trials are, okay, or how many of each trial. So my sample space over here is, I have 5 homicides. I have 12 drug offenses. I have 6 assaults. And I have 9 property crimes. That gives me a total, and they actually even tell me the total, a total of how many possible cases I could be assigned to. How many different cases are in that group?
32.
32. So what it is, guys, is you got picked for jury duty. Okay, you went and you got picked. And this has happened to me before, and you actually get picked. And here's 32 cases, and they're going to assign each one of these people to different cases. Actually, they're going to assign, 12 people to each case. Okay, is what they're going to do. So there's 12 times 32 people there in the room, and they're waiting to get their assignment. And so what it asks is, what is the probability that a juror gets assigned to a case that isn't a drug case? So if we base this off of the last formula I gave you, okay, what you're looking for is, well, it says probability not a drug case. That means you are actually looking for the probability of the complement of a drug case, right? That's what you're looking for. And that's going to equal 1 minus the probability that it is a drug case. Now, this is how they wanted you to work the example, okay? So we're going to work it that way, and then I'm going to show you could have easily just done it without working it that way, okay? Because if I go 1 minus the probability that's a drug case, well, how many drug offenses are there? 12 out of how many total? 32. So you put that in your calculator, and 1 minus 12 over 32 gives you 20 over 32, which gives you 5 over 8. Okay? Now let's say you don't like the old complement formula, bless you, and you don't want to use that, okay? So my probability that it's not a drug case is going to go like this. And you can do it like this for this problem because there's not a lot of numbers, okay? Well, how many aren't drug cases? Well, there's 5 homicides, right? That's not a drug case. Plus there's 6 assaults, plus there's 9 property crimes, all out of 32. 5 plus 6 plus 9 is 20. There's 20 cases. Guys, if there's 12 drug offenses out of 32, there's 20 that aren't drug offenses, okay? 20 over 32, and that does give you 5 over 8. Now, later on, we will discuss about events that are not independent, because I'm going to bet more than likely some of those drug offense cases are also assault cases or property crime cases, because usually there's some of those that all go hand in hand together, okay? And the homicide cases probably actually involved some of the, I mean, there's going to be some assault going on if a homicide occurred, you know. So they usually like to start racking up charges on a human, but we will talk about those kind of situations later on. 5 out of 8. All right, let's talk about empirical probability real quick. Formula and definition for empirical probability. Okay. I started not to give you the definition, but then you do have a couple of questions where it asks you to decide if it's empirical or it's theoretical. So I was like, I got to give you the definition. Empirical probability is based on observed frequencies. That is the number of times a particular event has occurred out of a certain number of trials. So we have the probability of E, or the probability of an event, is going to equal the observed frequency of the specific event over total number of trials. And sometimes they'll write it F over N. Okay? Okay, the next part you're not going to write. I'm going to, there's only one example. Oh, no, there's 2 examples left. Example 4 is long. The reason it's long is because it's a long word problem. It's not hard. But I'm not going to make you write it. I'm going to paste it on here. And then when I post the notes, it'll be there for you if you need to go back and look at it. It's over blood types. Okay? I'll let you finish writing that. And then if we don't have time for example 5, I'll write example 5 out for you and just post it on the notes. Okay? Actually, I just keep recording and y'all get up and leave at 11:30. Okay, we good? Can I flip? Mm-hmm. Good, Parker?
Yes.
Okay. I'm flipping. Okay. All right, let's look. 0232. Let me, that's not the right one. If I'm on, this is 10-1, right? Here we go. See, you didn't want to have to copy all this down. 10.1. Nope. I've lost you. Where did you go? There you went. There you went. Okay. Paste. All right, guys, we have, this is example 4. Let me write that at the top. Sorry about that. Everyone has a blood type that falls into one of 4 categories: O, A, B, or AB. When a blood transfusion is needed in an emergency medical situation, you might think that you'd have to get the same type as your blood, but that's not actually the case. The chart below describes which types can donate and receive various types of blood. Okay, so if you are O, you can donate to O, A, B, or AB. Okay, you can donate to all 4 of those if you are O. But now O can only receive who? O. All right, A can donate to A and AB. B can donate to B and AB, and AB can donate to AB. Okay, so AB, honestly, is the luckiest one of all because he can get anybody's blood. Okay, B can get 2 people's, A can get 2 kinds, and poor little O can only get O, right? So if you're O, let's hope you know you're O, and you wear something so that somebody knows you're O if you're unconscious in an accident and can't tell the people, oh, I'm O. Okay, let me go back right there. There he is. And so let me copy that. Okay, and then let me copy the other half. I told you this was a long little problem there. Copy. There we go. Yep. Okay, in a random sample of 500 people, 210 had type O blood. 223 had type A, 51 had type B, and 16 had type AB. First, set up a frequency distribution, then use it to answer the following questions. Okay, you need to write this part down. So on example 4, say example 4, and then you need to write what the frequency distribution looks like, because you will probably have to fill out a table. Okay? So we list the type, and then we list the observed frequency. If you are from stats, you didn't write observed, you just wrote frequency. And those frequency tables were much longer, and that probably brings back really sad thoughts to your life. So our types are, we got A, we got B, we got AB, and we've got O. It says, and then we've got the total. Well, we know the total. What's the total there? How many people were in the random sample? 500, good. And it said 210 had type O. So 210 goes across from the O. 223 had type A. 223. 51 had type B. And 16 had type AB. All right, there's your frequency distribution chart. Okay, short, simple. A says, what's the probability that a randomly selected patient's donor's blood can be given only to a patient of the same blood type? So you're looking at the donor chart up here. Who can only give to themselves? The same type as themselves. Which one? O can give to O, A, B, and AB. Look at the donor. Good, AB, good. Only AB can give to AB. So how many AB folks do I have? 16. Out of 500. This time they want a decimal. Tell me what that decimal is when I say 16 divided by 500. Good, 0.032. So about 3% of that population can only donate to themselves. Okay? B says, find the probability that a randomly selected donor's blood can be given to exactly 2 different blood types. Who all can give to 2? A and B can give to exactly 2. Okay, so I look, here's A, here's B. So I'm going to say 223 plus the 51 over the 500. That gives me 274 over 500, which does give me 0.548 when I put that in, because I know we're over time. Okay, 0.548. And then C asks me, what's the probability that a randomly selected patient cannot receive blood from a donor of the same type? Who can't receive blood from themselves? Anybody? No. Everybody can receive blood from themselves. Look, AB has a line coming from AB. See, if you go backwards. B, does he have a line coming from B? Yep. Does A have a line coming from A? Yep. And poor little O, he only gets O. Okay? So, what's the probability of that occurring? 0. Yeah, it's 0. You're not going to get anybody who can't get blood from somebody that has the same blood as them. Okay? That is the end of example 4. You guys can go. I'll write example 5 on there. Okay, so last one we have, guys, is example 5. And it says, if a die is rolled 1 time, find the probability of getting a number greater than 2 or an odd number. Okay, and so part of our Unit 1 dealing with set theory, as we discussed, comes back here. Okay, so if we're talking about OR, if you'll remember in Unit 1 in set theory, we had OR looks like this, not OR, intersection looks like this, and the union looks like this. Okay, so if you'll remember, OR went with union and went with the intersection. So what we have, because we have to be careful if there's any crossovers and what it means, this is getting us ready for the next couple of sections, is pretty much we can list all the sample space as a universal set, okay? And then you can split it up by what you want the event to be. So a die is rolled, so that means I have 6 numbers, 1, 2, 3, 4, 5, 6. And we're looking at the numbers that are greater than 2. So greater than 2 or an odd number. Okay, so the first thing we want to do is fill in that intersection. And so we want the odd numbers greater than 2. Well, that's 3 and 5. Okay, the other odd numbers are 1. That's the only other one. And the other numbers greater than 2 are 4 and 6. Okay, the only thing that's left floating out here in the universal is the 2. Now, notice it says or. Think about back what or went with. It went with the union. So that meant all of these. It meant everybody in greater than 2 and odd. So pretty much it's talking about everybody but 2. So when we find the probability of greater than 2 or odd, well, I know there's a possibility of 6 in my sample space because I can roll a 1, 2, 3, 4, 5, or 6. And then who's in the blue? 1, 2, 3, 4, 5. So my probability is 5 out of 6.